Good morning, everyone. Apologies for this slight delay. So this morning's webinar is on the OCS-I analog input module. It's roughly about 20 minutes presentation. And as usual, if you have any questions, you can put them in at any point and we'll get to them at the end.
Hello and welcome to today's webinar. Today we're going to be looking at the OCS-I Universal Analog Input Module. Let's get started. Let's look at our agenda for today. We'll start by talking about some of the highlights of the ADU100 module. Then we'll go through the different signal and sensor types that are supported by the module. We'll have application tips as we go, and then at the end we'll configure the ADU100 and we'll have a demonstration. We'll start by looking at some of the specification highlights. There are 4 channels in the ADU100 and it's built using a 16-bit A to D converter, which means it has a lot of resolution for most applications. It's quite accurate with a good specification of 0.2%, and it supports lots of sensor types from 4 to 20 milliamps or 0 to 10 volts, all the way to thermocouples, RTDs, and even millivolt signals. One of the best things about the ADU100 is that it is channel by channel selectable for the sensor that you're going to use, which makes it extremely versatile and economical. Now we'll look at some physical highlights. Like all OCS-I modules, there are diagnostic LEDs available on the ADU100. It has a power LED and an OK LED, and then it also has one channel status LED per channel for a total of 4. And what causes that light to turn up or to turn off varies by signal type, and we'll go through those as we go through the different signal and sensor types. Each channel on the ADU100 has 4 terminal connections, an A, B, C, and 0-volt connection. Those plugs are spring clamp style, so wiring can be inserted quickly and they're all removable. And all connections are labelled, which makes it easy to wire properly in the plant or in the shop. We'll start with the signal types of 4 to 20 milliamps and 0 to 10 volts, which are the most general purpose and common in automation. Examples would be pressure sensors, level sensors, and sometimes flow sensors, and there are thousands of sensors available which support these ranges. Generally, you should only choose to support 0 to 10 volts when it's the only output signal that's available for a particular sensor, as there are advantages to choosing 4 to 20 milliamps instead. Firstly, if you have a sensor that fails or a wire that comes loose, you'll be able to detect in 4 to 20 milliamps that you have a signal below 4 milliamps, which means there's a problem. Whereas if you have a 0 to 10 volt sensor that fails, 0 volts doesn't really tell you anything because 0 volts is a valid reading. Also, 4 to 20 milliamps, because it's a current, is much less prone to noise or voltage drop. Now we'll look at some application tips, starting with wiring. There are 4 terminals on each channel, A, B, C, and a 0-volt terminal. And depending on the sensor that's connected, you're going to find either the A, the B, or the C, or some combination of those will be used. Starting with the 4 to 20 milliamp and the 0 to 10 volt wiring, and you'll see that the A and the B are used for current signals and the B and the C are used for voltage signals. There are multiple different types of 4 to 20 milliamp sensors, as we can see on the screen. You have 2, 3 and 4 wire sensors that are available and are all supported. These are relatively low-level signals, and you should use shielded twisted pair wiring between the sensors and the ADU100 so you can properly shunt any EMI or RFI to earth ground if you properly drain the shield for the cable. Now we'll look at the readings that come back and what format they're in. Remember, we're doing analog to digital conversion, so we'll get a digital value back into our analog input register, and we can choose how we want that data to come back. With the highest resolution, we can choose 0 to 32,000 counts. If we want readings that are easy to deal with, we can do 0 to 1000 as the range coming back, but resolution will be lost in exchange for what will probably end up being extremely stable signals. On the left, we can see how 4 to 20 milliamp readings come back. You'll notice that 0 counts represents a reading of 4 milliamps and 32,000 counts represents 20 milliamps. However, you can still detect values below 4 milliamps. They're just negative all the way down to minus 8,000 counts, which represents 0 milliamps. So we can get high resolution by selecting the 4 to 20 milliamp range, but still detect values below 4 milliamps. Now, if you choose 0 to 10 volts or 0 to 20 milliamps, you don't get the same resolution, but you can detect all the way down to 0 with a reading of 0 counts correlating to 0 milliamps or 0 volts, and a reading of 32,000 counts representing 20 milliamps or 10 volts. So for current, we recommend 4 to 20 milliamp as the range you should select. And for voltage, we still recommend 0 to 32,000 as the range you would select. Next, we'll look at RTD temperature sensors. RTD stands for Resistant Temperature Detector, and they're one of the most common and most preferred temperature sensors. That's because they're quite accurate, easy to work with, and they aren't too expensive. The only real disadvantage of RTDs is the fact that they have limited temperature range. For example, if you want to read temperatures above about 800 degrees Celsius, you'll need to use a different temperature sensor like a thermocouple. Now we'll look at how RTDs work. RTDs are variable resistors where the resistance changes with temperature, and there are several types of RTDs which are defined by the material of construction and the resistance value at 0 degrees Celsius. The most common RTD sensor type is a PT100. PT stands for platinum, which is the material of construction, and the 100 means that the reading for PT100 at 0 degrees Celsius will be 100 ohms, which is a low resistance value. If you have a lot of wiring between your measuring instrument, like the ADU100, and your temperature probe, then you might have a few ohms of resistance in your lead wiring, which, if not compensated for, will cause an error in the reading. So any quality RTD measuring instrument will have the ability to work with 3-wire and 4-wire RTDs, and it sends out a small microamp current which it can use to measure and calculate the lead resistance of the wire. And it can subtract that out to ensure that the temperature reading that's reported is strictly the temperature at the probe. To wire RTDs, they use the A, the B, and the C terminal. 3-wire and 4-wire RTDs are the most accurate and they're wired identically, except with the 4-wire RTD, you simply tie off the fourth lead. There are some high-end scientific measuring instruments that will take advantage of that fourth lead fully, but you don't find those very commonly in industry. We'll look at the diagram at the bottom there, and that is a 2-wire sensor, which is a PT1000 sensor that has 1000 ohms of resistance at 0 degrees, which means that the resistance values are about 10 times more than the PT100. Because those resistance values are so much higher, the lead wire resistance is just insignificant round-off error, and so a 2-wire sensor is appropriate. PT1000 sensors have a much more limited temperature range. In many applications, you'll be tempted just to use standard RTE lead wire or just copper wire between the probe and the measuring instrument. If you have an application with a lot of noise, it is recommended that you opt for shielded RTU lead wire and properly ground the shield to eliminate EMI and RFI in your application as much as possible. For the temperature ranges that are supported, you can see there on the screen that the PT1000s have a more limited temperature range than the PT100s. You can select in configuration between degrees Celsius or degrees Fahrenheit for the format in which the temperatures come back, and they come back already in 10th degree increments. If you have an open circuit on your RTD, the status LED and the module will turn off. That LED will be on with 4 to 20 mA or 0 to 10 volt if your reading is above 0.2% of 0. Now we look at thermocouples, which were some of the earliest temperature sensors used in industry. They are relatively inexpensive and they have the widest temperature range possible. However, they are more difficult to deal with, which keeps them from being applied in a lot of different applications, and they can be susceptible to electrical noise, and we'll see why in a minute. Thermocouples make use of the material properties of metals. If you take two different metals and you join them at the tip, at the point where they're joined, a voltage will be generated that varies with the temperature. So that tip, called a hot junction, can be used as the measuring point for your temperature, and it will generate a different voltage as the temperature changes. One thing to consider is that the voltage generated is very small, and that's one of the reasons why thermocouples can be susceptible to electrical noise. Another thing that makes thermocouples more difficult to deal with is that when you take each lead of the thermocouple and you connect it to your measuring instrument, the ADU100 in our case, then you're also going to have a small voltage that is generated at those points, which is effectively error. So any quality thermocouple measuring instrument must measure the temperature at what's called the cold junction and calculate what the voltage loss is and compensate for it, so that the resulting reading that's reported is strictly the temperature at the hot junction or the tip of the probe. Now we'll look at wiring and application tips. On the right, we can see that thermocouples are wired to the ADU100 using the A and B terminal. There are two different types of thermocouple construction, ungrounded thermocouples and grounded thermocouples. With an ungrounded thermocouple, the hot junction is electrically isolated from the ground. So if the tip physically meets the machine or the measuring point, and that machine has a chunk of metal that is somewhere earth grounded, with an ungrounded thermocouple, the probe is isolated from the ground. Whereas with a grounded thermocouple, there is no electrical isolation between the measuring tip and the probe itself. If the probe itself touches earth ground, then you're going to have ground potential at that point. The ADU100 can handle both ungrounded and grounded thermocouples, but not every measuring instrument supports both. For instance, the Smart Rail thermocouple module only supports ungrounded, while the Model 5 XL Series I/O option and the XL Prime I/O option support both. For thermocouples, the extension wire is another factor you need to consider in your application, as you might be tempted between the thermocouple probe and the ADU100 to use standard copper wire to connect the two. But if you do, you will get a cold junction out in the field where it can't be compensated for, and readings will be off. Instead, we use thermocouple extension wire between the two, and that's true with any thermocouple measuring instrument. So if you're using a Type K thermocouple probe, you should use Type K extension wiring, and if you have a noisy environment, you should use shielded thermocouple extension wire and properly handle the shield. Next, we'll look at the values that are being reported by the ADU100. The range of values vary by thermocouple type, and we can see on the screen 8 different thermocouple types that are supported by the ADU100 and the temperature ranges that are supported in both degrees Celsius and degrees Fahrenheit. In the red columns, we see the decimal values that could be reported by the module if you have an open circuit condition. And in general, those values that are reported are larger than the highest range value that could be reported for that thermocouple type. The values are already scaled for temperature in degrees Celsius or degrees Fahrenheit increments. The thermocouple module only turns on the LED if that channel is enabled for thermocouple, so you can't use that LED for detecting an open circuit. That will be based on the readings coming back. Now we look at millivolt input, which is supported by the ADU100. Millivolt input's most common application would be load cells, which are force transducers, meaning they are mechanical devices that convert force to an electrical signal which can be measured. Sometimes you'll hear the term strain gauge being used, while strain gauges are actually internally part of the construction of the load cell. A load cell is an array of strain gauges. So we'll look into how load cells work. Electrically, a load cell is based on a Wheatstone bridge, and all the little resistors are individual strain gauges. The way a Wheatstone bridge works is that you have excitation voltage, which is the input voltage for the circuit, which could be 10 volts. So that 10 volts of excitation will excite the circuit, and then based on the gain of the load cell or the Wheatstone bridge, the output voltage will be generated. The gain varies by load cell, but it's usually around 2 or 3 millivolts per volt. The magnitude of the output of a load cell is going to be the excitation voltage times the gain. So in the case of a 10 volt excitation and a 2 millivolt per volt gain, you're going to end up with a full scale output of 20 millivolts. Now, is the ADU a good choice for load cells? Well, if you have an application that requires very high update rates and very high resolution levels, then you're going to be better off with a dedicated piece of equipment that's going to interface with your load cell and will come up with a reading that you can pass on via another signal type or industrial network back to the OCS. However, if you have routine requirements and you don't need especially fast readings with high resolution, then the ADU100 will be a good choice. It is possible that your excitation voltage that's the input to the load cell could drift. Generally, with load cells, you're going to be selecting an excitation supply with good specification so that you get a good constant voltage that doesn't drift. But to make sure, you can connect your excitation supply to another channel of the ADU100 and measure that voltage if the excitation voltage is 10 volts or lower. So that's one way you can use the ADU100 to not only measure the output of your load cell, but also verify the excitation voltage. Now we look at how values are reported back and something called effective resolution. So if you're using a load cell range with an ADU100, you're going to select the 0 to 32,000 scaling range, as it's the only real practical range available, and 0 millivolts represents 0 counts, and 60 millivolts is represented by 32,000 counts. But what is effective resolution? We'll look at real-world applications with, for example, 2 different load cells and 3 different excitation voltage levels. So some common load cell gains are 2 millivolts per volt and 3 millivolts per volt, and some common excitation voltages are 5 volts, 10 volts and 15 volts. You're going to get an output that ranges anywhere from 10 millivolts up to 45 millivolts, depending on the combination of gain and excitation voltage, and in the third column on the chart we see the amount of counts over the entire range of the load cell in that scenario, because it's going to be a subset of 32,000 counts. If that number of counts is plenty for your application in terms of the resolution you're looking for, that's another reason why an ADU100 could be an excellent choice. Also, the ADU100 will turn on its status LED once a signal greater than 0.2% of the reading is present. So those are the different signal and sensor types available to connect to the ADU100. Now we'll see how to configure the ADU100. So we start in Zscape and we go to Hardware Configuration area. Next we go to the CAN-IO tab that contains the OCS-IO rack, and we double click on the CNX base here just to see how that was configured. So we can see we assigned it a name, it was assigned a network ID, we assigned a status variable, and then we have to assign a starting IQ AI and AQ real world IO address for each of the 4 different IO types for the base. So that's how it works. Today we're focusing on the ADU100. So in the rack of 8 modules total, including the CNX, there are 2 ADU100s, and we'll just look at one of them. So there are different things that we can configure on a module by module basis. We have an analog filter that can range from 0 to 7, the value of 0 is no filtering. And then as you increase the value, you get more stable readings that take longer to respond to changes. So it's a compromise between reading stability and reading response time. For most applications, 3 is a good middle ground. So we'll go down to the bottom now and look at the input update time. And that can be as fast as 10 milliseconds and go up from there. We've set it to 25 milliseconds. This is how often the ADU100 is going to send new readings over CAN to the OCS controller. Then we have our channel by channel configuration for signal and sensor type as well as data range. So we'll look at the different signals that are available here. So we have on the screen here voltage and a couple of different current options and 0 to 60 millivolts for load cells and all those different thermocouple types, 2 different RTDs, and of course disabling the channel altogether because disabled channels will not be scanned. Once you select the particular signal or sensor type, then you can select a data range now for voltage, current and millivolts. We would recommend selecting 0 to 32,000 as it gives the most resolution. And then for temperature type sensors, we have our choice between Celsius and Fahrenheit values, which come back in 10th degree increments. So that's the configuration of the ADU100. Now we'll look at the bench. Here we have a full rack of OCS-I with the 2 ADU100s in the middle. We're using the EXLW for demonstration purposes. And then we're also using this high-tech simulator to simulate all these signals we'll look at now. These ADU100s were not factory calibrated, so maybe a small bit off, but for demonstration purposes, they will work. We'll start with 4 to 20 milliamps, and we're at a mid-range setting on the simulator of about 12 milliamps. So let's see what that looks like. Mid-range should be about 16,000 counts, and we're pretty much there. And we are simulating a 10 to 100 pounds per square inch type sensor with a 4 to 20 milliamp output. If we go down to 6 milliamps or so, what should be a fairly low setting, you can see the readings respond. And if we go up to full scale at 20 milliamps, we see they respond as well. Now, the time it takes them to respond is influenced by the filter setting that we set up in configuration. The lower that filter number, the faster it responds. So now we need to switch to voltage range to see how it works. And to do this, we move the probes from the milliamp position to the voltage position. And then we need to move our output of the simulator to the next voltage channel. And then we change the simulator configuration from milliamp to voltage, and we'll go to say a mid-level range of 5 volts. And then we'll take a look here. Now that we have a good connection, we can see mid-range we're within a few counts of 16,000. If we go down to say 2 volts or 20%, we should see it react appropriately, and it is. And here we're simulating a level of 0 to 1 meter, and at 20% we're at the 0.2 meter level. Now we'll go up to a full 10 volts on the simulator and watch it go up to around 32,000 counts. So that's voltage. The next thing we'll look at is thermocouple. So we need to add the thermocouple probe here to the simulator. This thermocouple probe doesn't use copper outputs here, it uses a special thermocouple extension wire cable that connects to the thermocouple channel. Again, we need to switch the simulator from voltage to thermocouple. Then we'll go to 50 degrees Celsius, and we can see what that looks like on the screen here. Again, close to 50 degrees, you can see the count is 10 times the actual temperature because it's in 10th degree increments, and we chose degrees Celsius here. Now we'll go to 500 degrees, and you can see we respond based on our filter setting, and we're up close to 500 degrees. So that's thermocouples. Next we'll look at RTDs. So we disconnect our thermocouple probe here, and we change the simulator from thermocouple to RTD, which we have done. And we'll go with a say 50 degree setting, and we must remember to move our probes. Now we go to the RTD, and you can see that we've had a little trouble with our probes there, but we're making our way to 50. The reason it's taken so long is it was basically an open circuit, so it was at full range, and it's taken a while to get down close to 50. And again, the unit is not factory calibrated. So now we'll turn it up to 500 degrees and we can see if we can get up near it. Again, this could really be improved with some factory calibration on the RTD. So the last range we'll look at is millivolts. For this, we need to change the simulator from RTDs back to voltage, and we'll set it for 5 millivolts. And then we must remember to move the probe to this last position here, and we'll take a look at 0 to 60 millivolts. So again, we are coming up on 5 millivolts, and we can see the raw counts here. Now, we're scaled 0 to 32,000, which correlates to 0 to 60 millivolts. So you can see we're about 5 millivolts, and we'll move that up to 20 millivolts. And we should see our reading respond, and it is. And again, we can go all the way up to 60 millivolts with this particular range, but with most load cells, they're going to be in the 20 millivolt or 30 millivolt range most of the time. so there's our millivolt range. So it's a versatile module that can connect to many sensor types, and each channel can be selected on an individual basis, and configuration is extremely straightforward when performed in Seascape. Later in 2023, there will be the additional option with Seascape that will allow you to change sensor types in the field. At the moment, you have to have a different Seascape configuration for thermocouples and RTDs, but in the future, after that new version of Seascape is released, you'll have the ability to make that change in the field. So that concludes our webinar for today. Thank you so much for listening, and the Q&A session will begin shortly.
Okay, so that was that, nice and straightforward. I'm not seeing anything in just yet. So next week we will go through the digital I/O modules and then into configuration, and that'll be the last run of our OCS-I/O selection of webinars. Okay, other than that, thank you all for joining us this morning. I'm not seeing any questions in. So thank you, and we'll see you next week. Have a good day.